Welcome everyone. In this lesson, we're going to see how to calculate a definite integral using the fundamental theorem of calculus. So you know it's important. It's called the fundamental theorem. And let's start by looking at what this theorem says. And there's actually a couple parts to this theorem. We're going to be looking at part 2, the second part. So nothing like starting with the second part first. But in any case, this is the main part of the theorem we're going to be using in this course. So let's read through it. Suppose we have a continuous function little f, and it's continuous on this interval from a to b, and this function has an antiderivative which we call capital F. Then we're going to calculate the definite integral of function little f from a to b, and the notation that we're going to use for this definite integral is right here. So it looks like our indefinite integral notation, except it has these, what we're going to call limits of integration, these little numbers on the integral sign here. And so how we actually calculate this definite integral is we find the antiderivative and then plug in the endpoints. So this right here, this is our definite integral. And we're going to be investigating what this actually is. So there's a definition for this involving limits. So we'll see the precise definition of this later on. And then we'll see some interpretations of what does this definite integral represent. Right now, we're just going to get some practice calculating these things using this fundamental theorem of calculus. And it's going to feel very similar to the process for what we were doing for indefinite integrals. The only difference is there's one extra step where we evaluate. So let's kind of go through the procedure here. How do we calculate a definite integral using this fundamental theorem? All right, so step 1. We have our definite integral that we're going to calculate. So it's the integral from a to b of f of x dx. This is our definite integral that we're interested in. Again, we'll see interpretations, what this thing actually is. Right now we're just getting some practice calculating it. The first step is look at this function, little f of x, find the antiderivative. So this is what we've done so far. For our antiderivative and indefinite integrals is looking at just this function, getting the antiderivative. So that's step 1. Find the antiderivative. Now, there's more to it here because we're actually going to do some evaluation. So this is a definite integral. So we're actually kind of looking at this function little f of x over the entire interval from a to b. And what we're going to do is we're going to evaluate this antiderivative capital F from x equals a to x equals b. And so the notation here is we use this big vertical line next to our antiderivative to indicate evaluation. So we're going to evaluate, and then we write down our upper limit on the top and our lower limit on the bottom. And the way we plug in, the way we do the evaluation is right here. So it says take the top number, the b, plug it in first. And then take the lower number, a, plug it in second, and subtract. So that's the second step, is we do the evaluation. And there's a specific, whenever we have subtraction, there's a specific order in which we have to do it. So it's the top number minus the bottom number when we plug in. So the top number here goes in first, bottom number goes in second, and then we subtract. So you have to do it in that order. So, the order matters. All right. So this thing's called, let's go back to our integral here. we kind of use a lot of the same notation and terminology, so as we saw with indefinite integrals. So we still call this big squiggle. We call it an integral sign. It's kind of an elongated S, actually. We'll see why later on. But this is what we call the integral sign. Same as indefinite integrals. We have our function we're integrating, which we call the integrand. And then we have our differential dx. And that's all the same as what we saw with indefinite integrals. Now, the thing that's kind of new is these little numbers. And we call these the limits of integration. So we have our upper limit, which is on top. And then we have our lower limit, which is on the bottom of our integral sign. And there we go. So that's kind of the only thing new here is we're looking at this function, little f of x, over some interval from a to b. And we're going to be calculating this definite integral. And the one kind of important thing here, well, not kind of, it actually is important. We need our function, in order for this theorem to work, we need our function to be continuous. So that's something we want to check. We want to check that our function is continuous on the interval from a to b. So it has to be our function, the function we're integrating, has to be continuous on this interval. So kind of look for those usual things like division by 0 or 0 inside a log function, things like that where you might run into trouble with continuity. So we want to just keep this in mind. We want the function we're integrating needs to be continuous on that interval. All right, so this is the fundamental theorem of calculus. We're gonna use this to calculate these definite integrals. We'll see what those are over the course of the bunch of lessons. We'll see some interpretations of what this definite integral is. Right now, we just want some practice calculating these things. So there are a few notes. So the notation is very similar to what we are doing with indefinite integrals, but there are some key distinctions here. So when we write down an indefinite integral, the notation, again, is very similar. It's the integral of f of x dx. Now the difference here is there's no little numbers. So what does this represent? What does the indefinite integral represent? Well, the result is it's a function. This represents this. We use this notation to represent the antiderivative, and it actually represents all antiderivatives for this function little f of x. So actually, this represents kind of a whole class of functions, and so we normally put plus c at the end because we know all the antiderivatives are very similar to each other. They just differ by a constant. So this is where we put plus c at the end when we have our antiderivative, when we're calculating our antiderivative. So if we have this indefinite integral, the result is going to be a function with plus c at the end. Now, what happens with a definite integral is now we're calculating the integral from a to b of f of x dx. So again, similar notation, but here the result is a number. So for indefinite integrals, we should be ending up with a function as our answer. And for a definite integral, we should be ending up with a number as our answer. And for purposes of calculating a definite integral, we don't actually need to use plus c. So it's not wrong if we use it in our work. It ends up just getting canceled out as we might see. So we don't normally use it here. All right. So that's just a little note there about our plus c. And actually, you know what? Let's see why it gets canceled out. So here we have, you know, two antiderivatives, two different antiderivatives. And let's say it was the antiderivative of some function little f of x. So let's call this one f1, and let's call this one f2. And let's calculate the antiderivative. Now it could be either one of these, but let's say we just throw in our plus c. So these are two specific antiderivatives. Let's just use that plus c to represent all the antiderivatives. Let's see what happens if we throw that plus c in there. So we're going to evaluate this antiderivative from x equals a to x equals b. How does the fundamental theorem work? Well, you take the top number, plug it in. So we get f of b plus c. Take the bottom number, plug it in. We get f of a plus c. And then we subtract. And then what happens is if we distribute the subtraction here, subtraction is going to go on to this f of a, and then it's also going to go on to this plus c term. And so we have plus c, and then we're subtracting, and then we have another c here that we're subtracting off. So the c's cancel. And what we're left with then is just f of b minus f of a. So for the purposes of calculating a definite integral, we don't actually need to use the plus c here, because no matter how you do it, it ends up getting canceled off. So going to this little picture, if we were integrating, we could have used either one of these antiderivatives and we would have ended up with the same result, essentially. So just a little note here about plus c, and it ends up getting canceled off. All right, so let's try an example. That's what we're going to do next. We'll try an actual example integrating a nice polynomial power function and actually using this fundamental theorem to calculate a definite integral. So we'll see that next.